I'm here at the eScience Institute working with Ariel. My background is astronomy, so I'm kind of out of my element here as far as the domain science. But I've spent a lot of my time during my astronomy PhD and in the years afterwards working on kind of more general machine learning approaches to various areas of science, from astronomy to neuroscience and other domains that I've worked with. And I've also spent a lot of my time on kind of the open software in general. And Scikit-learn is one of the projects that I've been working on since about 2010 in some form or another. And it's a nice kind of standard Python library for machine learning that you can make use of in your own science as well. So yeah, my goal today with this tutorial is I really want to kind of get into the basics of machine learning, like how you should think about the question of like what machine learning is, how you should think about data in terms of machine learning, like how do you represent your data as it goes in. And because I'm going to be kind of going through those kind of essential pieces of machine learning, we're going to be using today mostly kind of toy data sets. So my hope is that based on these few hours of thinking about and manipulating little small data sets and thinking about how you represent features and those sorts of things, that you'll be able to jump from here into kind of more complicated and more relevant things as you learn a little bit more. And I think later in this week and into the next week, there's going to be some talks about specifically applying some of these ideas within neuroscience with Python packages that are built on top of Scikit-learn, like DiPy and NiPy and some of these other more specific things. So that's the whole, that's the broad umbrella of what we're doing here. I want you to walk away from this afternoon knowing what machine learning is, kind of knowing how you're gonna arrange your data to be used in machine learning, and knowing the vocabulary that you can kind of use to build up your knowledge from there. So all of this tutorial is in Jupyter Notebooks. It's all available on GitHub at this address. But I believe you also have a Jupyter Hub instance where everything has been loaded already for you. So if you're connected to Jupyter Hub, you should be able to get into this. Are there special instructions for that, Ariel, to access this material?
Folder on your home directory.
Okay, folder in your home directory on Jupyter Hub, and all these notebooks should be in here. So hopefully what you can do is get the notebooks loaded up, and the index is old. It had to be converted from the old notebook format. But the rest of these are new and up to date. You can jump into the notebooks, and right here, I think I have in here enough material for 5 or 6 hours, and we only have maybe 2.5 hours, so we're not going to cover all of this. But we'll get through the first few notebooks, and then kind of into some of these in-depth notebooks here. And just as a broad outline, these preliminaries are like installation stuff, and I'm basically going to skip that because you have that all on your Jupyter Hub. But these two notebooks under introduction are where we're going to cover how to think about machine learning, how to think about what it is, how to think about what the data should look like, the principles you should think of when using these things. And then from there, I have a couple dive in a little more in depth into a couple algorithms that you might find useful within the machine learning space. So support vector machines, random forests, principal component analysis, k-means, Gaussian mixture models. And then there's another notebook here on model validation. So we'll see how far we get in that. But if we don't cover everything in here, then I've sort of designed these to be standalone, so you can jump into it yourself. So let's click on preliminaries, and I think here is just talking about the goals and the schedule of what all of this will take, and the packages that this depends on. So if you're using Jupyter Hub, all of these should be installed already. Okay, and one thing I want to point you to right off the bat is the Scikit-learn website. So if you take a look at this, the Scikit-learn website is really an amazing resource. I think of it as kind of like a free, it's almost like a free online textbook about machine learning. And I'll be referring to this throughout as we go through the tutorial, but basically the Scikit-learn website, one of the philosophies of Scikit-learn has been to create really, really extensive and well-written documentation for everything within the machine learning space that Scikit-learn implements. And what that means is that you can go on the website, use it not just as a reference for code, but also as a place to learn about these concepts a little more. So make use of that. We'll see a little bit of that later. Okay, so let's go back to the index and jump into this machine learning intro right here. So the main goal of this first section for the next 20-30 minutes or so, I want to talk about the definition of machine learning. I want to talk about data representation when you're using Scikit-learn for machine learning, and the basics of the Scikit-learn API. So really quick about Scikit-learn. Scikit-learn is a package that was started, I think, back in 2007 or 2008. As a Google Summer of Code project. And then it sort of died and languished for a while. And around 2010 or so, Gaël Varacou and a couple other people from INRIA in Paris decided to get it back off the ground again. And Gaël, is he here yet, or is he going to be here later? Tomorrow, okay. So Gaël's great because he basically has masterminded this project and gathered people who have contributed to it and turned it into this really amazing resource for doing machine learning in Python. And it's also great because Gaël is a neuroscientist, so you know that the stuff he's building here is relevant for all of you. And so since then, it sort of got off the ground in 2009 or so, I think, something like that, 2010. And since then, it's turned into this kind of standard tool that is used in Python, that it's pointed to by people not in the Python world as a good example of an open source project for its documentation, for its API and things like that. And the API of Scikit-learn that I'm going to tell you about in a minute is one of the best features of it. We'll see this fit, predict, transform API that Scikit-learn has. And that's been, over the past few years, really influential within the Python world for various implementations of machine learning libraries. So if you get used to the Scikit-learn API, there are a lot of other libraries out there that have adopted the same API. So you can drop these tools into your machine learning workflow with Scikit-learn with minimal hassle. So that's the library. So Scikit-learn is a machine learning library. So what is machine learning? It's kind of this hyped up language, hyped up term, but essentially the basics of what machine learning is machine learning is a way to specify models that have tunable parameters, and you tune those parameters to data that you look at. And then that lets the model make statements about other data. So the statements that model makes might be predictions about some label for this new data. It might be statements about how some data is related to new data that you've seen. And effectively, so that's what machine learning is. It's models with tunable parameters, and you tune those parameters based on data that you've seen. I just realized I need to clear all outputs, and I'm going to execute this as we go along. So the first thing, as an example of what a machine learning model is. So this is a nice example of a machine learning model. So let's say these points, these red points and blue points, represent data that you've gathered. You have one measurement along the x-axis, one measurement along the y-axis. These red points are labeled number 1, blue points are labeled number 2. This could be any sort of data that it's kind of a generic data set. The machine learning model here, the goal of the model might be something along the lines of saying, well, we want a model that given a new point that's gray and we have no idea what the label is, should we call it red or should we call it blue? Right? You can think about this in any context. It could be maybe red is spam email and blue is a good email that you want to put into the inbox. Or maybe red is tissue that shows a disease and blue is tissue that doesn't show a disease. And so we want a machine learning classifier that based on this data that we know the labels for, will be able to come up with another one. So this is a simple machine learning model. We draw a line between the two data sets in two-dimensional space. And then we can say anything that falls below the line we'll label red. Anything above the line we'll label blue, and then we have our automated model, right? And this might seem like really, really incredibly simple. I want to show you though that this isn't just like some figure that I made in PowerPoint or something. This is actually a Scikit-learn model here. So we have, I made some blobs. I use a stochastic gradient descent classifier. I fit it to the input data. I created a grid and then basically plotted the model using that grid, using this contour plot right here, and then scattered the data on top of it. So this is not just like an illustration. This is an actual model. And the benefit here, like you could obviously do this by hand if you wanted to, right? If you had two-dimensional data and you were looking at that, it would be pretty easy to draw a straight line and split that. And that's what a lot of scientists have done for a long time with low-dimensional data. But the benefit of this kind of model is that as you're scaling to very large numbers of points or very large numbers of dimensions, you can use the same routine and the same algorithm to get a separator. So if instead of having x versus y two-dimensional data, if you had 1,000-dimensional data, and you had to draw a 999 dimensional hyperplane in that 1,000-dimensional space to do this split, that'd be really hard to do by hand. But with these algorithms, they scale, they work regardless of the dimension in most cases. So we could use this same algorithm to do that. So this is a task that in machine learning is known as classification. It's because we have kind of a yes or no answer or discrete labels for our points. Another type of model that you can see in machine learning is known as regression. So in this situation, what we're imagining is that we have some x variable that we've measured, and we have some y variable that we've measured, and we want to know, given some x value, what is this continuous y value? And in two dimensions, the way that you can do that, one way that you can do that is fit a line to the data, right? So every time you're doing linear regression, fitting a line to data, you're essentially doing a machine learning model. You're saying, given my x value, what's my prediction for what the y value should be? And again, this seems really simple, right? In two dimensions, you can draw a line. Some of you could probably even write down the equations that you can use to solve that line, right? We learned this in our kindergarten statistics class. But the nice thing about these sorts of models within a machine learning context is when they're defined the right way, they can scale up to a large number of points and large number of dimensions. So you could have, instead of one x value and a line that predicts a y value, you could have 1,000 x values and you need a 1,000-dimensional hyperplane that fits those in order to predict the y value. So that's the power of this machine learning approach here. And again, this plot right here is not just it's not something that I made in Adobe Illustrator. This is an actual plot that from a linear regression model fit by Scikit-learn to this data. So broadly, the reason I wanted to go through those examples is just to get you to start thinking about what it means when you're doing machine learning. Machine learning doesn't necessarily mean that you're training a car to drive, although that's part of it. It can be as simple as fitting a line to data or splitting apart two different clusters with a line. So any questions about that? This is just a way to to not scare you with with complexity. Machine learning can be very simple, but it can scale to very complex things. So the next thing we need to think about is how we represent data. So let's say you have some data and you want to fit a model to it and train this model and use Scikit-learn. The way that data is generally represented in Scikit-learn and in most machine learning libraries is with a matrix and a vector. So here in the features matrix is essentially the data that you're going to observe about anything in the world that you want to make a prediction. And the features, we usually talk about features in terms of or the features matrix in terms of the number of samples, which is the number of rows right here, and the number of features, which corresponds to the number of columns. So what's a sample and a feature? A sample, so each row of this matrix right here corresponds to one thing that you're observing. So it could be one email that you're trying to classify as spam or not. It could be one galaxy that you're trying to predict the distance to. Or it could be one, I don't know, what's a neuroscience example? It could be one 3D voxel image that you're trying to classify as a good or bad. Do you do good or bad? I don't know. it's one entity that you're trying to classify or make predictions about. And corresponding to this row right here is a target vector, and this is the label. In a supervised learning context, we'll talk about supervised in a second. In a supervised learning context, these are the labels you want to predict. So this would be something that tells you, yes, it's spam, or no, it's not spam, or this might tell you the distance to the galaxy, or this might tell you if your voxels are good or bad. And so basically the row of the feature matrix and the element of the target vector correspond. Now, so what are the columns of the feature matrix? In the feature matrix, each column is going to correspond to one uniform measurement that you make of every single thing in your data set, every single object. So in an email, this first column might be the number of times the word Viagra appears, right? And then that might be a good indicator of whether the email is spam or something like that. Or in astronomy, this first column might be the flux that we measure through a particular filter. Or this first column might be the value at a particular voxel in a scan. Right? And the key thing, though, is that each column is measuring the same thing for every object. So you've organized your data in terms of observations per object, where every row is one object and every column is the same observation you're making across the data set. Okay? Does that make sense? Yeah. So this is how Scikit-learn organizes data, and it's also how data is organized if you're generally using R libraries or libraries in another language to do machine learning tasks. So a simple example, and I apologize if any of you have been in machine learning intros before, because you've probably seen the iris data set lots and lots of times. So this is a classic data set that's due to Fisher. It's almost 70 years old now. But this iris data set, the idea is this. We basically want to train a machine learning model to identify iris species. And we might want to do this because hiring a botanist is expensive. And if you can replace the botanist with an algorithm, then you're much more efficient, and your science, you can progress in your science more. So we go out and we gather a whole bunch of data about flowers out in the wild, and we get some trained botanist to look at those flowers and tell us what their species is. And then based on that training data, the idea is we could go out and gather some more data about other flowers, and instead of bringing the botanist with us, we just use the algorithm to predict what the botanist might have said had they seen the picture, right? So the question here is we have, in this data set, we have 3 different species of iris. We have the setosa, we have the versicolor, and we have the virginica. And we want to figure out features that we can use to predict those species. So what might the what would a row of the matrix correspond to here? What's the sample in this case? What's that? Yeah, so that might be a feature. That might be a column of the matrix. Like if you look at a pixel of each image. But what's the row correspond to?
Flower.
A flower, yeah. So it might be, each row might be an individual flower. So you go out and observe 700 flowers, and that means you have a matrix with 700 rows. And now, so the next thing though, what does each column correspond to now? Well, you said it could be a pixel of the image, right? So yeah, so that's a way to do this. You could make up a feature matrix where each column corresponds to a pixel. So you take the top left pixel of every image, then the next pixel over, the next pixel over. So if you have if your images are 1,000 by 1,000 pixels, then your matrix would be 1,000,000 columns because you need one row for each pixel. What else might we do for features here? Oh yeah, that's funny you mentioned that. So he said petal length. So yeah, you could go in here and you could use a ruler and you could measure the length of each of these petals, and you could get the petal length for every flower and put that in there. This is something that's kind of known as feature engineering, right? We're deciding on something based on presumably our knowledge of what's important about flowers, and deciding what we could measure that's in common for every flower. Any other ideas? Petal length, pixel values? Colors, yeah. So you could use some sort of like photometer that quantifies the reflectance spectrum of a certain part of the flower, right? And so that would be a way to get numerical data that's like the same. You're measuring the same thing for every flower. So these are all great ideas. I should mention one thing: if you're measuring the pixel values, it's really complicated, right? Because like let's say you're looking at the pixel values of this iris versus the picture versus the pixel values of this iris picture. You're comparing, like if you take this pixel right here, you're comparing the backgrounds to the petal. Right, so it would be, you would need a lot of data in order to use those pixel values and get a really good classification, because you have to cover kind of not only the space of all different iris variations, but you have to cover the space of orientations and where they appear in the image and things like that. So in general, using like engineering kind of more specific features for things can be a better approach. Yeah, so we talked about this number of samples versus number of features, and in the iris data set, which you can import in Scikit-learn using this load iris function. Effectively, what it is the where I write this down. Yeah, so the features in the data set are the sepal length, the sepal width, petal length, and petal width. How many have seen this data set before? Like 3/4 of people. You all held your tongue really well when I was asking about the features, except for one person. It's all right. Yeah, so petal length, petal width, sepal length, sepal width, and we have 3 different species that we're going to predict. So if we look at this data set, first of all, looking at the iris.data, it's a 2D matrix that's number of samples by number of features, and we print those out and we see 150 samples and 4 features. So that's 150 different flowers, and for each one we've measured these 2 widths and 2 lengths in centimeters. And if you look at one row of the matrix, this is, to this algorithm, this is everything we know about the flower. It has a petal length of 5.1, sepal length of 3.5, petal width 1.4, sepal width of 0.2. So we've kind of like taken everything about that flower that exists and encoded it into these 4 numbers. So that's why it's really important that you make sure these numbers are meaningful if you can, that the features you're pulling out are meaningful. And now if we look at the data.shape again, so this is the number of samples by number of features. We look at target.shape, and this is a length 150 array. And in this case, the target is just a bunch of numbers, where 0 corresponds to setosa, 1 corresponds to versicolor, and 2 corresponds to virginica. All right, so that's what we've taken with our training data. We've reduced it down to these 150 by 4 numbers plus a length 150 array. All right, so when you're doing some kind of machine learning task like this, it's often helpful to visualize this data to kind of see what's inside it. And so with the iris, I put together this matplotlib function here that lets you do a few things. And you can visualize, say, sepal length versus sepal width and color it by species and see what the distribution is. If we change the indices here, so this is sepal length versus petal length, and you can see in this projection of the data, it's pretty clear that the setosa are really well divided from the rest of the data. But the virginica and versicolor, these are a little bit more mixed here, right? So just visually looking at this, you might expect that, that an algorithm would have an easy time pulling out the setosa by itself, but might be a little bit more confused between the virginica and versicolor. It might be a little more uncertain what those classifications are. Right, and you can play this game of looking at all pairwise features. You could even, if you wanted to invest in it, you could do some sort of scatter plot of all the features pairwise together with multiple columns. And that's a good way to kind of get a sense of what's going on in your data, to see if there are outliers, to see if there's anything you're missing here. So I put in here a quick exercise to do this, but I guess I already did that, to look at these various features together. And if you look at all of them together, you can kind of see that, you know, in all the pairs, the virginica and versicolor are mixed and the setosa is separate. So that's the iris data set, and that's just a way to help you start thinking about how you can structure your own data to be used in these kinds of algorithms. Okay. So Scikit-learn has these other data sets available that you can see if you use the tab completion of IPython or Jupyter. So there's this newsgroup data set, there's housing prices, there's LFW, which are labeled faces in the wild. It has like a whole bunch of politicians from the 90s. It's a pretty interesting one. So if you've ever wanted to separate Tony Blair from George W. Bush, you can do that with this data. Other faces, there's some species distribution data, and a lot of this data that's used here, that's within these data set access, is the data that's used in Scikit-learn's documentation. So as you dig through the Scikit-learn website, you'll see a lot of these various data sets and some machine learning algorithms on them. Cool, so any questions about data in Scikit-learn? All right. Yeah. Sorry? Imbalanced data, like what? Oh, so if you have missing features within some of the data. Yeah, so that can be a little bit difficult. There are, if you're missing part of the features, there are a couple ways to deal with that. Generally, what I'm going to talk about today is sort of assuming that you have all the data there, but you can do various approaches. Like the simplest thing that people do is just imputation based on the mean of the rest of the sample, or something like that. So, like if you lost the measurement of the sepal length for one of the irises, then you could use the average of the sepal length for everything that's the same species. And sometimes that works. Sometimes it's not so good. There are more sophisticated things you can do, like you can actually model the distribution of your data and try to impute things that way. But in general, the standard machine learning algorithms treat that as like a pre-processing step and assume that you have full information on all your features. So the algorithms I'm going to talk about today require that you don't have any missing data in your data set. Yeah?
And what the balance is in terms of the neighborhoods? Who's supervising?
Yeah. So we should clarify. You used the word imbalance, and that has a Yeah. So imbalance has a specific meaning in machine learning that's different. But yeah, so for missing data is that. If you're asking about imbalance in labels, like for example, maybe you have 1 million Setosa irises and you have 2 versicolor irises. That's a very different thing, and you have to be careful about how you train your algorithm. And that's like in section 3 or so. So I'm going to talk a little bit about that, but yeah, at this point we're just talking about the data itself. Yeah, but so these are great questions, and these come up in practice, but we'll get there. All right, so yeah, let's close this and go to this basic principles notebook right here. So now we've talked about data. We've talked about getting our data into shape and thinking about that. The next thing I want to talk about is basic principles of machine learning, like how you should think about the machine learning problem and what classes of problems you can solve with the machine learning. So I'm going to clear all outputs here and import some things. Now, in Scikit-learn, I talked a little bit about the importance of the Scikit-learn API a little while ago. So here I want to dig into the Scikit-learn API and familiarize you with how to think about fitting a model in Scikit-learn. So the first thing is that in Scikit-learn, every time you want to fit a model to data, the first thing that you do is import some class, some Python class that implements that model. So here's an example where I'm going to import a linear regression model. Right, and in Scikit-learn, here's this linear regression model is something that just defines. You can think of it as like a pipeline that defines what it's going to do with the data, what it's going to fit about the data, and what it's going to get out. It's like this abstraction of a model on your data. And the first thing that we do with this model is we instantiate it. And now this instantiated model, you can think of it as like you're deciding what flavor of linear regression you want to do on your data. So we have these instantiated models generally have a number of different what we call hyperparameters in here, or implementation details that you choose right in the beginning. And so for example, with this linear regression, basically fitting a generalized line to data, we can ask it to fit the intercept or not, so that like if you're fitting a line in 2D, do you want it to go through the origin, or do you want it to go through some other part of the y-axis? You can ask it, tell it whether you want to normalize the data before fitting. This njobs lets you do things in parallel if you're set up for that. You can use multiple cores on your machine. But basically the point is here that you make all these decisions before you even think about the data, before the model sees anything about the data. So we've created this linear regression model. Now, the next thing we need to do is when we've decided what flavor of model we want to fit, what kind of linear regression we want to fit, we can give it some data. So for example, I'm going to do something really simple. I'm going to do x values between 0 and 9. I'm going to do y values that are 2 times x plus 1. And you print these, and we have this array of x values and an array of y values. And we can even plot them and see that they're right in a line here. So this is just the simplest set of data that you might want to fit a line to. And now remember that we're trying to use basically x as the features and y as the labels here. We're given x, we want to predict y. So we need to get this into the form of the data that we talked about earlier. So we need, for x, we need a number of samples by number of features matrix. So what's the number of samples here? 10, yeah, and what's the number of features for x? 1, yeah, because we're taking this single column of data and we're trying to predict the y value. So we need to take x and we need to reshape it into a 10 by 1 matrix. So you can do that in NumPy in a number of ways, but adding a new axis is a great way to do that. And now if we print this, we see that we have the features matrix, 10 by 1. We have the samples matrix, length 10. And now we're going to take our model and tell our model about the data. Fit the model to data with this model.fit function. And so what does that do? What that does is we have model up till now was just sort of defining the terms that we want to use, defining the flavor of model we want to use on our data. And when we pass the data to it, there's something going on internally. It's kind of like a black box. We're throwing our data into the black box. The model's doing something with that data. Different models will do different things. But for the linear regression model in particular, it's using that data to compute something called a COEF, a coefficient, and it's computing an intercept. And in this case, the coefficient and intercept from describing a simple line, we see that the coefficient is 2 and the intercept is 1. So the model has recovered this 2 times x plus 1 model. So it's basically recovered the input that we did right here, 2 times x plus 1. So this is, I'm emphasizing this because I think it's useful to keep that in mind, that the model object itself doesn't know anything about the data when you instantiate it, but it's when you call the fit function that you actually apply it to data. And this means that you can pass different models around and be kind of entirely agnostic to what they are. And we'll see an example of that later. And so I didn't mention here this, if you have an underscore at the end of a class variable like this, that's an indication in Scikit-learn that it was fit to the data. So anytime you see something with an underscore at the end, think of a parameter that was fit to the data. So that's the basics of the Scikit-learn estimator, and we'll see more of that as we go on. But in that context, I want to jump in now to talking about a little more about classification and regression. So the real difference here is, I mentioned this earlier, but classification and regression. With classification, you're trying to predict some sort of discrete label, like this iris is a versicolor or virginica or setosa. With regression, you're trying to compute some sort of continuous quantity, like predicting the y value given the x value for a line. And that's the real distinction there. And the reason that distinction is made in machine learning is because kind of the class of models and the way you approach problems is a little bit different if you have a continuous label versus a discrete label. So as an example of classification here, I want to show you a k-neighbors classification. So the idea with k-neighbors is relatively simple to explain. If you have a bunch of data and you have a new data point and you want to know what the label is, you compute the distance between that data point and all the ones in the training set. Look for the nearest ones, and whatever those labels are of the nearest points, you assume that's the label of the output. Right, so this is great, and this is nice to do in Scikit-learn because you can do it in a few steps. So we're going to first import our neighbors and data sets, load our iris data, pull out the two matrices, the features matrix and the target matrix. And now here we have our class, our k-neighbors classifier class. We're going to decide what class of k-nearest neighbors algorithm we want. And in this case, the free parameter is the number of neighbors. So we say KNN is number of neighbors this. And then once we have our model decided, we can fit it to data with the fit function. And now this is the next part of the API that's important, is the predict function. So now given a new piece of data, we go out into the field, we find another iris, we measure the petals and sepals, and we want to know what the species is. We can pass that to the predict function, and it'll tell us what the predicted species is. So this is kind of like the basic machine learning workflow, right? You fit a model to data, and then you predict it on new data that you don't have a label for. Now, one thing that I've glossed over here is this as you look at these models, the parameters that you pass here are relatively important. Like if we ask for the one nearest neighbor, it'll tell us that this is virginica. If we ask for 5 nearest neighbors, what did we get? We got versicolor. If we ask for 50, I wonder what it'll be. Oh, it's also versicolor. So this simple workflow kind of glosses over an important step, which is how do you choose these aspects of the algorithm that you have to choose before you even look at the data. And this is known, I mentioned this earlier, but this number of neighbors and the things that you pass here are known as hyperparameters, because they're kind of like parameters that control what the parameters are that you end up fitting to the data. And this idea of choosing hyperparameters in an informed way is where the rubber really meets the road in machine learning. And we'll talk a little bit more about this in the model validation section later. But this is the workflow that you should get used to if you're fitting a machine learning model. You instantiate the class, fit it to data, and predict on some new data. There are other things you can do as well. So there's a predict proba method, which allows you to get a probabilistic prediction about the data that you're looking at. And here with number of neighbors equals 50, the probabilistic prediction you get is that there's an 18% chance that it's the first species, 62% chance it's the second, 20% chance that it's the third, given this model. So that can be pretty useful to kind of get a sense of uncertainties in prediction as you're going about this. So now I've been talking a lot, and I want you to try to do this yourself. So instead of using what did we use here? Instead of using a k-neighbors classifier right here, I'd like you to do the same thing but use the SVC, which stands for support vector classifier, and see what you get for this example right here, this 3542. What does the SVC say that this label is? I'll give you a few minutes to jump in and try that. Has anyone predicted the answer? All right, so when I typed this in, I basically followed exactly what was done up here. except instead of a neighbors.kneighbors, I use the SVC classifier right here, called fit, called predict, and figured out from the target name what the result is, and I got Virginica. So how does this compare up here to the neighbors? Up here it said versicolor. Down here it's Virginica. You know, if you start tweaking the C parameter, you get something different. Versicolor, right? That says Virginica if you have the C's small. So yeah. So what I wanted to get across with this is the fact that you can basically, once you have this this procedure in mind, this fit predict, or instantiate fit predict in mind, it doesn't matter. You don't really have to think much about what the particular classifier is. You can just apply that. But if you look at, like if I do Shift Tab right here, I can see all the different options I have in this classifier. Kernel equals RBF, degree equals 3, gamma, coefficient. These are all things that need to be tuned somehow to make the model the best it can be. Right? So you can, to an extent, you can treat these things as a black box, but if you're going to go beyond anything but the most basic toy problems, we can't treat these really as a black box anymore. And this is why later on, after we finish this basic principles notebook, we'll take a break and we'll come back. I have a few sections on going in depth on some of these algorithms so you can understand exactly what the algorithm is trying to do inside that black box, and how you can start to think about tuning it. Okay, but back here though, these are the basics that I want you to get working with your fingers. Fit and predict. Instantiate, fit, and predict, and we'll do some other things. So another thing, that was a classification example. Let's take a look at a simple regression example. So here's something, before we saw some points that actually lied on a nice line. These points don't lie on a line, but we still have a situation where given an x value, we might want to predict a y value. And this is some kind of noisy data that would let us do that. So let's do, as we did above, and plot a line of best fit. So we're going to do model equals linear regression. We're asking for a linear regression model. We're going to fit it to our data. And now this time when we predict, in order to plot a line, we're going to just create a grid of data points here that will predict what the result is. And now we can call model.predict on that grid of data points. And we can plot the input data. This x.squeeze takes the column matrix and turns it into just a vector, so it's nice to work with. And xfit.squeeze is our grid. So we plot that, and we see there's a line to our data. So if, according to a linear regression model and the assumptions that it makes, this is the best fit line to our data. And if we have an x value of 0.4, then this will predict that the y value should be 3, right? So is that a good model for the data? What do you think? Yes or no? Good model? From your silence, I think you know the right answer, which is nobody knows. This is not enough information to answer the question of whether that's a good model for the data, right? Maybe the error bars on the data are this big, and so this is a huge outlier that's not properly fit by the model. Maybe the error bars are bigger than the screen, and this model is just modeling the noise in the data or something like that, right? We don't know whether this is a good model for the data unless we think more deeply about what the data is. But Scikit-learn, these machine learning models will just take inputs and spit out outputs, and at some point you have to start thinking about them. Yeah.
How do we tell the linear regression model about errors in the data, about error bars?
Yeah, so that's a good question. This comes up a lot when scientists start using machine learning, because generally models like in Scikit-learn and in other machine learning contexts don't take into account error bars. And there's no, like for example, support vector machines, there's not really a good method to put in error bars on your data. So this is something I think Guile will address in more detail as he kind of jumps into kind of more of the advanced topics in machine learning based on the simple stuff we're doing here. But it's not an easy answer, unfortunately. So thanks for bringing that up. I can tell you in my own work in astronomy, I tend to not use straightforward machine learning models because of that, because errors are very well quantified in astronomy data and very important. So I generally move into more of like a Bayesian context where you can write down specific models that take into account your exact expected error distribution and that sort of thing. So hopefully, I'll defer to Guile on that, and hopefully he can tell you about it tomorrow in this context. So, Scikit-learn, if you have a simple model like this, the nice thing about Scikit-learn's API is you can change the model really, really trivially and do something different. So, for example, I copied and pasted this linear regression code. And instead of linear regression, I'm going to do from sklearn.ensemble import random forest regressor. So this is a different type of classifier. It's a different type of regression algorithm. So I'm going to switch out, and instead of saying linear regression, I'm just going to do random forest regressor here. Keep all the rest of the code the same and plot it. And this is the random forest model, right? So is this a good model for the data? Definitely maybe, right? It depends it depends what you're trying to do with the data. It depends what your goals are, what your error bar is. In this case, the random forest model is much more flexible, and it can do things like get very close to certain data points. But it might be that if these data points are very noisy, you might not want the whole model to get pulled down towards them just because they exist down there. But the beauty of this is we can do this whole thing, and we can switch out the models just by switching out the class that we're using, and the API, the interface for all of them, is the same. So this is the Scikit-learn API, this fit and predict, and then later we'll see transform and other things that a lot of the machine learning world has adopted. Okay, so. What I'd like you to do now is take this example that we've done here with the random forest regressor and look into some of the hyperparameters. You can find that either on the Scikit-learn website or by using Scikit-learn's or by using IPython's documentation utilities, and change some of the hyperparameters and see how that affects the fit. So see if you can get a random forest that looks closer to this linear regression, like a very simple model, or if you can get a random forest that looks much more complicated, and just to get a sense of what changing those parameters might do. Did anybody find a hyperparameter that kind of seems to adjust the model complexity and decide how much it can wiggle around? What's that? Max depth? Yeah, so what did you find there? Max depth. Yeah. Yeah. Yeah, so if you change the depth to 1, it doesn't wiggle around quite as much. But if you do the depth of 10, then it does wiggle some more. Did anyone find something else that's relevant in that? Ooh, min samples per leaf. Equals 1. Yeah, so if you do a small min samples per leaf, it's really wiggly. If you do a large one, then it's, oh yeah. You basically get a straight line model. Yeah, so we're going to get into what actually is going on under the hood here as far as random forests. But it's nice to know that generally when you're setting these hyperparameters here, generally what you're doing is you're kind of choosing the level of complexity you're allowing in the model. So in this case, if we do min samples per leaf equals 1, we get a really wiggly model. Or 10, we get a very straight model with, at this point, it's just a constant model, right? So that's, and if we do 5 somewhere in between, then it can be constant for a while, then wiggle a bit. So this kind of thing is just a useful general way to think about those hyperparameters. It's like tuning knobs to tune your model complexity, and that's where they get relevant. Okay, so any questions about regression before we move on to the next thing? Yeah.
I have a question about the bootstrap samples. Turn it off the
Oh yeah.
data.
If I do what? Bootstrap equals false. Oh yeah. So yeah, effectively so what's going on here is that Bootstrap is kind of a way to add some randomness within your estimator. And here, the reason this is fitting perfectly is because what Random Forest is doing is it's storing all the data and then kind of creating a model based on things in the neighborhood of that data. So when you do Bootstrap equals false, it's able to like exactly replicate every data point. And so this might be a useful model, but if you had another point in here, if you left this one out and then tried to predict with it, it wouldn't be fitting that point perfectly. Right, so this is, we'll get into this later, but this is a model that's overfitting the training data, right? So that's a good point. And if you do Bootstrap equals true, effectively what that's doing is it's leaving out a little bit of the data, so the model can't predict the data points perfectly anymore. Yeah. Any other questions? Yeah. All right, so the last thing in this introductory section that I want to talk about is unsupervised learning. So up until now, we've been talking about what's known as supervised learning. And when you hear supervised and unsupervised, supervised, you should think I have data with labels, and I'm trying to predict those labels. And that could be classification, where the labels are discrete, or regression, where the labels are continuous. But you're trying to predict labels. In unsupervised learning, you don't have any labels on your data, but you're trying to like predict aspects of the data set itself without any reference to labels. So an example of that is dimensionality reduction. So you might say, let's say you have 1,000 observations about each object you're looking at, 1,000 features, and you're trying to figure out which of these features is important in some sense, or which of the features encode redundant data that you can you can toss out without losing any information. That's known as a dimensionality reduction problem. Another type of unsupervised learning algorithm is clustering. So if you have a whole bunch of unlabeled data, but you want to know which objects are similar to each other without reference to any labels, clustering is something that you can do. So let's look at some quick examples of that. So dimensionality reduction, this is where we're trying to take higher dimensional data and project it down to lower dimensions so that we can either reason about it or compress the amount of information we're using or pre-process it for particular other machine learning algorithms, that sort of thing. And we can do it similar to above. We're going to import the PCA classifier. We're going to instantiate the PCA classifier with some sort of hyperparameters. In this case, the hyperparameters is, this tells us the percent of the variance in the data that we want to maintain. We're going to fit it to the x value alone. Now remember, before we did fit to x and y, supervised algorithms will fit to both both the feature matrix and the target vector. Unsupervised algorithms fit only to the feature matrix. They don't have any reference to the labels that you might have. And now instead of predict, we're going to do PCA.transform x. And the result, remember the input x is 150 by 4. The output is 150 by 2. So what this has done is it's taken our 4-dimensional data and it's tried to find a 2-dimensional representation of the data that somehow maintains aspects of the input. And now if we scatter this is what it looks like. So this is our 2-dimensional representation of the 4-dimensional data. And if you want to know what the x and y components are, within PCA here the x component is 0.36 times sepal length minus 0.082 times sepal width plus 0.857 times petal length. It's basically a linear combination of the parameters. And that can be, depending on what you're doing with the PCA, that can be useful or not. But the point is that what you get out here is a lower dimensional representation that can sometimes be easier to visualize. So this lets us see a little bit in one screen what's going on with the whole 4-dimensional data set. Now similarly, we can do a clustering. And clustering, like I said, is another unsupervised dimensionality reduction algorithm that in this case will actually let us label the data without putting any labels in. So here I'm going to start with a k-means cluster with 3 clusters, and k-means has a degree of randomness to it, so I'm going to set the random state to 0 so that we get the same results every time. And then I'm going to fit it to the data, and you might in supervised you might do x comma y, but in an unsupervised case the k-means has no information about the labels of the data. And then here we can predict what the labels are on the x given no input labels. So this is kind of the magic here. And what k-means is doing then is taking this input data, and it's decided that all these points here on this side are similar and should have the same label. And then it's taken this clump of points here and drawn a line between them and asked and said that these are similar and these are similar right here. So the point of clustering approaches is that you can just look at the distribution of the data set as a whole and label points as similar or different. Now again, this is a little bit weird because for k-means, you have to set the number of clusters to start with. So if you ask for something with 2 clusters, it'll look like this. And it kind of does this weird thing of pulling these points over to that cluster. Or you can ask for 20 clusters if you want. You can find 20 clusters among your data set right there. So there's some degree of kind of having to choose beforehand what you're looking for. So it's not, k-means in particular is not really automatic in that, but there are other clustering algorithms that are a little bit better about choosing the correct number of clusters. And again, if you go to the Scikit-learn website, there's there's really great examples of clustering in scikit-learn. So we looked at the k-means algorithm, which is most similar to this leftmost column right here. And I love this visualization because it shows you all the different ways that clustering algorithms approach different weird data sets. And so you can see some of these actually choose, like dbScan chooses a different number of clusters depending on what data you put in. So right here it's choosing 3 clusters, right here it's choosing 1, and right here it's choosing 2. Whereas things like k-means, you actually have to decide how many clusters there are beforehand. So yeah, the scikit-learn documentation is a great place to learn about these sorts of things. And I should say that in my own research in astronomy, I've found these sorts of clustering approaches and other unsupervised machine learning approaches to be the most useful in actually dealing with real-world data. Because the straight prediction pipelines are not always, you know, you can't always learn a lot about data by trying to just throw data into a black box and get out a label. But you can learn a lot about data by fitting algorithms like clustering and dimensionality reduction that sort of learn something about the distribution of the data set and then give you interesting numbers out. So in my own work, I've really enjoyed looking at these sorts of algorithms like Gaussian mixture models and manifold learning and principal component analysis and things like this. So scikit-learn has all of those. So just as a quick recap of this, the estimator interface. Models have this fit method where you pass in the data. For a supervised model, it'll be fit on x and y. For an unsupervised, it'll just fit on x. In supervised estimators, you have a predict method. You might be able to do a predict probabilistic output if you have for certain models. And then there's a score method and these other things that are kind of standard across estimators. And then for unsupervised estimators, you might have a predict method for clustering, or you might have a transform method for dimensionality reduction. And then there's also things like, for some algorithms, it's much faster to do the fit and the transform at the same time than to do them at different times. So sometimes there's a fit transform method that'll do the same thing except much more quickly. So I'm going to just, because of where we are in time, I'm going to skip the model validation for now. We'll come back to that. But what I want to show you is how you can take all of these things we've been talking about, this supervised and unsupervised learning, and put them together to do something that's a little more interesting than just fitting iris data and lines and things like that. So to show you like what you can do with a data set that's looking a little bit more like a real world problem. And the data set that I want to look at is a data set with digits, handwritten digits. So essentially, this is the most basic form of the optical character recognition problem. So what we have is this. We have a whole bunch of pictures of digits that people have written, numbers 0 through 9. We have little snapshots of them. And we want to train an algorithm that will look at a snapshot of a digit and tell us what number it is. Right? So this has some nice real-world applications. And the data here within scikit-learn is nice because it's already cleaned up and kind of centered for us, and that's why it's the most easy version of this problem. So we have a whole bunch of input digits, and each one of them is an 8x8 grid with numbers representing the amount of ink in that grid. So it might be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And each one has a label that tells us what the true value is. So here what I actually did is I imported the load digits data set and looked at digits.images. And the images is a 3-dimensional array. It's 1,797 digits, each of which is an 8x8 grid there. So we need to figure out what features we're going to use here. And similarly to what someone suggested for the iris data set, we're going to actually use the pixel values themselves. So each image is 8 by 8 pixel grid, and you can count, that's 64 pixels in there. So we have 64 features for each image. So this means that our data set, our features matrix, should be a 1797 by 64 array. Now we could reshape these images using NumPy to do that, but the nice thing is that the digits data set has this view of the data in it already. So if we look at digits.data.shape, that's the 1797 by 64, and the row of the digits is just the flattened out array. If we look 005139, that's the first row of the image, 005139. And if you stare at this long enough, you can sort of convince yourself that this one is an image of the 0, right? Because it has no ink in the middle, but it has ink around the edges. Right, so that's how we've encoded these things. So this, oh yeah, and then the target is a length 1797 array that just tells us whether it's a 0, 1, 2, etc. Right. So this is right here is our first relatively high dimensional data. This is a 64-dimensional data set. So if you want to start out visualizing this would be 64 times 63 different XY scatter plots that we'd have to look at to see all of that. That's a lot of data, and it's really hard to, in general, if you get more than a few dozen dimensions, it's really hard to visualize the data because we can't think much beyond 2 or 3 dimensions. So this is where unsupervised learning, something like dimensionality reduction, can come really useful. So I'm going to import an unsupervised learning algorithm called ISOMAP. And I'm going to instantiate that model and say that we have 2 components. And so that'll be the model. And then when I'm fitting the data, in this case ISOMAP, it's much more efficient to fit and transform at the same time. So I'm going to call this fit and transform method that will take the data, fit it, and then transform it down to this number of components. So now we have this, oops, I added a character there. Now we have this projected data, which is 1797 by 2. So we've taken those 64 dimensions, we've squished it down into 2 dimensions, which is something we actually can visualize, right? So we'll scatter plot this. We take the first column of the projection, second column of the projection, color it by the targets, and then I'm going to play around with the appearance and the color map and things like that. And this is what we get. This is our digits data projected down into 2 dimensions. And I really love this example here because what this does is it shows you, number one, that the digits in this 64-dimensional space, the digits are pretty well localized, right? Like all the zeros are basically nearby each other, and all the 4s are really nearby each other. But it also shows you that there's some sort of predictable relationship between the digits, right? Because the zeros here are right next to the 6s. That sort of makes sense, right? Because if you draw a 6, you could imagine doing a sloppy 6, and then kind of it turns into a 0 if you make the 6 if you make a sloppy enough 6, that sort of thing. But there's no way to go from a 0, for example, to a 1. Like nobody is drawing a 0 in a sloppy way that makes it look like a 1. So you can use these sorts of dimensionality reduction techniques, let you kind of understand the relationship between pieces of high-dimensional data. And one reason I love this sort of thing, this is the ISOMAP algorithm. It's a manifold learning algorithm. And my first author paper I ever wrote was taking a manifold learning algorithm and applying it to 4,000-dimensional galaxies from the Sloan Digital Sky Survey, and using that to understand kind of broad relationships between this data set of 1 million points in 4,000 dimensions. So it's kind of, and actually that was, I didn't mean to get all autobiographical, but I get excited about this. It was that paper that made me, that caused me to dive into implementing manifold learning in Python. And then manifold learning in Python was my first contribution to Scikit-learn. So that's how it all comes full circle. But yeah, this is the digits data set, which is a little easier. So looking at this, we can reason about the data, but we can also kind of see that in the higher dimensional data set, we might expect that a properly trained algorithm would be able to separate these digits pretty well, right? So let's do some classification on digits. The first thing I'm going to do, and I glossed over this because we didn't look at the validation section, but I'm going to split the data into a training and testing set. And the reason we're doing this is basically because we want to be able to train the model on part of the data and evaluate the model on parts of the data it hasn't seen yet. So if I look at the training set, I've pulled out 1,347 of these examples, and I'm going to leave aside 450 of them to see how well the model is doing. And we could use any number of classification models right here. I'm going to use something called a logistic regression, which is a little bit confusing because it's not a regression model, it's a classification model. But for historical reasons, it's called logistic regression. I'm going to instantiate it and then fit it to my training data, X-train and Y-train. And then finally, I'm going to predict on the testing data and see how it is. So we run this model, and we get some predicted outputs. So let's look at Y predict. So this is a big array of predictions of what digit we're looking at for that testing data. And now we might want to see how accurate it is. We can use an accuracy score, and we find that in this case our model has predicted with 95% accuracy the correct digit given an input. And then something else that's useful is looking at something called a confusion matrix. So this is like given this input, the input is 0, 42 of them were correctly identified as 0. But given the input of 1, 45 of them were correctly identified as 1, but there's a few 3s and a few 8s and a few 9s. So this shows us where the algorithm got confused between different classes. And just to help see that a little more, it's nice to be able to visualize the confusion matrix and maybe see what it is. And basically, the confusion matrix, if it's dark down the middle, it means you're doing well. So that's a way you can evaluate how your model is doing. Another thing that's nice is to be able to actually visualize the results and see where the model is failing. So here, the green numbers are ones that were predicted correctly, and the red numbers were ones that were predicted incorrectly. So you can see like this is a 6 that the model predicted was an 8. Here's something the model predicted was a 7, might be a 3. Yeah, I'd guess a 3. So some of these you can see it's not trivial to decide. Like this right here, this model said that was a 1. It looks like the artist formerly known as Prince, maybe. I don't know. So you can zoom in there and kind of see what's going on with the model. So. Yeah, the interesting thing to me here is that even with this really, really simplistic model, right? Like, how many lines of code did we do? We took about 6 lines of code to split the data and to train and predict the model. We have something that's really kind of pretty sophisticated and compelling, right? We've trained a computer to look at a digit and recognize what digit that is. And this is the power of machine learning, right? All we're really doing here is some high-dimensional generalized version of drawing a line between two blobs. But we can do that in very few lines of code very quickly and start predicting something that's like actually useful in the real world, right? So That's the end of kind of this introduction to machine learning for the first half of this time. We have, I believe, coffee is going to be out in about 3 minutes, so we have time for some questions. And just to give you an overview of what to expect after the coffee break, after these basics, what I want to do this afternoon is dive into a little more in-depth what's going on with some of these algorithms. So I'm going to talk about support vector machines and random forests, which are two really important classes of supervised algorithms where you can predict labels from data. And I want to dive a little bit into principal component analysis, k-means, and Gaussian mixture models, which are some important classes of unsupervised models that will help you kind of learn about the structure of the data without reference to any data labels. And also, if we have time, I don't think we'll have time to go into model validation in depth, but I think I'm going to return to that model validation section that we skipped over for this first part, because that's an important part of this. So yeah, any questions in our last 2 minutes before the break? All right. Yeah.
Do you have any comments on where Scikit-learn's linear regression machinery kind of does overlap with stats models, OLS machinery?
Yeah.
Why and where one would use one or the other? I mean, there's a lot of areas of non-overlap between these tools, but there is a segment where those two pieces of machinery have similar coverage.
That's a great question. So if you didn't hear, the question was, where does Scikit-learn's linear regression overlap with stats models, OLS, and other linear regression routines? The way I like to think about it is in a machine learning context, the model really is a black box. You don't care about model parameters. So when you're fitting a linear regression in a machine learning context, what you care about are the predictions. And you reason about everything based on those predictions, not based on the model parameters. In a stats models context, that's more of a statistical modeling paradigm where the model itself is meaningful, where you're trying to, like when you fit the slope, you're extracting the slope and the uncertainties on the slope, and that's telling you something about your model or your data. So that's where I draw the line between those two. And where they intersect is a lot of them are fitting the same classes of models. But in stats models, you're focused on the model itself, whereas in machine learning, you're focused on predictions coming out of a black box. Does that make sense?
Yeah, and just to follow up on that, given that a lot of our concerns here, and also in astronomy and other areas of scientific research, are in a sense about understanding. I mean, we're not only interested in whether the blue or the red background on the website drives sales high or low.
Yeah,
right?
yeah.
Because that's a case where the only thing that matters is the prediction, and as long as it's good, who cares how we get it?
Yeah.
We achieve the sales target that we have in mind, for example. In our case, using the word our as science broadly understood, we do care in a sense about understanding what underlying natural, physical, human, social phenomenon is happening. Where do you see then kind of that perspective from Scikit-learn in a scientific context, and when we teach these tools to scientists?
Yeah, it's funny you bring that up, because I was just remembering that last time I was in this room was at a physics conference where I have a book called Statistics, Machine Learning, and Data Mining in Astronomy. And the title of my talk was Statistics, Data Mining, and Machine Learning Don't Work in Astronomy. for exactly this reason, because a lot of these tools are developed in the context of, like what you say, where the results are all that matter, and the model is sort of this thing that you can ignore. But in science, you can't ignore the model. The model is where all the interesting things are happening in general. So this is, I think, why in my own science, the unsupervised learning methods have been more useful, because they're a way of unsupervised learning kind of, you care about the model a little bit more. It's aspects of the model itself that's interesting. And in the supervised context, like labeling data, I honestly haven't found many uses for these kind of things within my science. I know there are situations where that can be really useful. Like I'm working with someone, for example, who's trying to train honeybees to respond to certain behaviors. And it's really, really useful in that case to like be able to recognize when a honeybee is near a flower and whether it's doing a particular thing. And that's a perfect supervised learning problem. But that's, again, a case where you don't really care about the models, you care about the output, and then you're kind of interpreting responses to outputs. So that's something within the neuroscience context. I'm hoping that Gael can comment on that a little bit tomorrow when he dives into the more domain-specific versions of machine learning. But it's a very useful observation that supervised learning is not always that relevant to scientists who really want to understand data and understand models and not treat them as a black box. So I don't know if I answered your question, but let's take a break, and why don't we come back in here in about 15 minutes, and we'll dive into some of these estimators in depth. All right, the mic is back on. Sorry about that. Yeah, so Python Data Science Handbook. Most of this material, but a little more fleshed out if you're interested. Okay, so we talked about the basics in the first part. I wanted to say this morning, but it was this afternoon. How you represent data, how you think about the Scikit-learn API. Machine learning models are black boxes, and in a machine learning context, you're just really thinking about what the outputs are, not really about what's going on inside the box. But now I want to open that black box a little bit, because by understanding what's happening inside these algorithms, it can help you do a better job of reasoning about when you might want to use one algorithm or another. And one place that I want to bring up first, if you search scikit-learn flowcharts, there's this really interesting section in the Scikit-learn docs called Choosing the Right Estimator. And I'm not going to jump into this entirely, but this is the kind of thing that having a deep knowledge about what these estimators do can help you in figuring out what to do. And the funny thing about this flowchart here is it was created by Andy Mueller kind of as a joke. Like he drew this thing and he thought like, haha, this is so funny, let me tweet this out to my friends. And everyone around the world started like copying it and making their own version of it and like talking talking about how great it was. So then it became this official flowchart for Scikit-learn. But the idea is like you start here, and if you have greater than 50 samples, no, then get more data, right? You start over. But if you have, greater than 50 samples, then are you predicting a category or a quantity, right? It's classification versus regression. Do you have labeled data? Here's the classification. Do you have unlabeled data? Then you're into clustering. And it points you to a bunch of different examples of what you can do with certain data sets. So like if you're in the classification realm and you have labeled data, you have less than 100,000 samples, then the suggestion is to use linear support vector machines. And if that's not working and you have text data, then use naive Bayes. Or if it's not, then use k-naive classifier. So this is a way to kind of like dive in and see what might be useful, and give you an idea where to start. But if you can learn a little bit about what's going on under the hood, then you can make those decisions more effectively. So let's think about what's going on under the hood here. I'm going to click on this support vector machines in depth. Clear all outputs so we can start from scratch. Okay, so support vector machines are this class of model that you can use for either classification or for regression. So you can predict discrete labels, or you can predict continuous labels. And it's a really kind of cool algorithm when you start diving into it. So let's think about support vector machines and motivating them. That yellow is not very great, isn't it? I'm going to do a different color map to see if we can. No. Blues, will that be good? Is it capital? Blues? No, that's not good. Hey, let's do everyone's favorite, jet. Jet works. Yeah, so we have some data right here. And this is, again, stripped down to kind of a low-dimensional example with a very small number of classes. And we're looking at two blobs of data. So earlier we saw that one way you can define a classifier is by just drawing a line between these and saying everything on one side of the line is one class, everything on the other side is the other class. Right, and that's a nice way to do it. But the question is, how do you draw that line? Right? So you could draw several different lines on here that all perfectly discriminate this data, right? Depending on which way it is, a data point in the middle here would be classified differently. But for the training set, we don't really have, if we're just looking at a line, we don't really have a good way to choose between those. Does anyone have an idea what you might do to try to decide which of those lines is better than the other? Any thoughts? Well, one thing you might think of is like if one of these lines is getting really close to one of these points, then it's probably not the best line, right? You might want a line that's a little bit farther from points. So you could choose a whole bunch of candidate lines and penalize them based on how close they get to points on either side. And that's kind of the intuition behind support vector machines. Is you're drawing a line between the data, but you're penalizing the line if it gets too close to one of the clusters. And the way this penalty is applied is by doing something called maximizing the margin. So in support vector machines, you're not just drawing a line, you're drawing three lines. You have three parallel lines, one on either side with one in the middle. And the margin is this distance from the edge to the center. And basically you're trying to draw these thick lines between your data set in a way that the margin is maximized. So if we look at these three candidate lines that we put in, we have a narrow one, a medium one, and a large one. And this large one is the one that support vector machines chooses. And that's really the intuition behind it. You know, the rest is just like mathematics of how you do that effectively and how you compute that efficiently and make sure that you find the correct line with the maximized margin very quickly. Now, yeah.
For the margin, you're just essentially going to the data point for each class that's closest to the line.
Yeah, that's the way to think about it, is you choose an orientation of the line, and you kind of go as far up as you can until you hit a data point, and as far down as you can until you hit a data point, and then drawing the line right there.
So what if that data point is an outlier, though? Is there a way to try to take that into account?
Not really, because you're sort of taking the data at face value. Well, I'll get to this a little bit more, but there's a little bit later. But there's a way to sort of let the margins bleed into the clusters a little bit. So for example, like what you're probably thinking of is like if you had one pink point that was sitting down here, right? Then you wouldn't have any like clean margin between the points. But we'll see that in a second. Yeah.
Are common statistical methods for minimizing the influence of outlier cases acceptable or compatible with this? So like you could Windsorize something on a data point on a given dimension. Is that okay in this case, or? You
could do that kind of thing as like a pre-processing step. Yeah.
But the results you get would still be valid, right? As long as you get it responsibly.
Yeah, I mean, the validity of results is an interesting question in itself. But yeah, the results would be valid in the sense that you could put data in and get numbers out. And then you'd have to decide whether you believe those numbers the same way you do with any model. Yeah, good question. So, yeah, so this is the essential idea, is that you're trying to draw a line with a maximized margin in some case. And support vector machines, what the algorithm does is it uses some tricks in order to do that minimization as quickly as possible and find this best result. So if we're going to fit a support vector machine to this data, the easiest way to do that is to import this SVC, support vector classifier. This one, because we're fitting lines between the data, it's a linear support vector machine, so we can say kernel equals linear. And then this little CLF right here is something that I use often just as a shorthand for classifier. CLF is classifier. And we do CLF.fit x and y. And now we have this fit model. And then this is just a function that does a bunch of matplotlib manipulation and lets you actually draw the support vector model, so to draw the central line and then the edges of this margin right here. So you can see that effectively what this model has done when I'm plotting the decision function is it finds a line between these data sets that has the maximized margin. And now if we were to ask about a new point and say, is something right here, should that be yellow or pink? It'll be yellow, and if we have one above, it'll be pink. And then kind of in the middle here, it'll choose whatever is above or below that line, right? Okay, so that's the support vector machine, but this model is not particularly, actually, what was I getting at right here? Oh yeah, so I wanted to show, oh yeah, that's right, I have this. Why, I think I need to change this to make this a continuous thing. So one of the features of support vector machines that's really interesting is it has kind of the properties of choosing a median of data, in that it doesn't really care about the extreme values at all, but what it cares about are the values that are closest to the middle. So this is a little widget that lets me dynamically add data to the data set and fit the support vector machine to each data set. And what you notice is that most points, when you add them, it doesn't affect the model at all, right? It's only when you happen to add a new point right towards the middle that the model gets affected by that. And you can see some of the points are actually actually bleeding into the margins a little bit. So it's using this more generalized version of the margin that lets things be a little softer. But this is actually a really nice feature of support vector machines, because what it means is that if I had 1 billion points on top and 4 points on the bottom, it doesn't, in a sense, it doesn't really care about all those extra billion points. It only cares about the ones that are closest, and it won't. The model won't really be affected by those outliers on the upper side. So it's and this is one of the reasons that support vector machines can be as powerful as they are, because they're kind of robust in that way.
Can you, so you give, this is maybe putting you on the spot a bit, but a real-world example of where support vector machines are really, really good, and a real-world example of where this feature and the fact that most of the data isn't sort of used is bad. Sorry.
No, I can't do that right now. Yeah, I can't. Yeah, that's a good question. Yeah, I don't have a good answer for that right now. Sorry about that. Real world example. So I can contrast it with other things. So for example, there's this method called naive Bayes that basically computes the. You want a real world example, not a theoretical discussion. No.
Don't worry, sorry, that's everything else.
Yeah. Well, does anyone have ideas about that? Yeah.
I contrasted with clustering, where so in a clustering algorithm, you get some evidence about what is a typical instance. So you're classifying your two kinds of lilies, and rather than define it by the lilies which are mutants at the edges, you define what a lily is here and there with a clustering algorithm. And SVMs give you no insight, really, into the structure of your data. They only find boundaries.
Yeah, that's a good point. Did everybody hear that? The point was that the SVM, since it only concentrates on boundaries, it has no real idea of what a typical instance from each cluster is. Is that fair? Yeah. Okay. Yeah.
Perhaps in a similar line, sometimes when you face this kind of problems, the points are very, they overlap a lot.
Mm-hmm.
So in reality, even if you can draw a line, even if it's not a non-linear problem, you will not be able to start drawing margins of that very widely. Right?
Yeah, yeah.
The points are all together. Uncertainty towards the victim. So does SVM come with a way of addressing that? Ideally, I would like to pay more attention to the extreme values.
Yeah. So the question is similar to the question we had before. Is that when things start overlapping, there's this sort of intuition that I gave doesn't work, but also if you want something that pays attention, quote unquote, to the very extreme values, SVM is not going to do that. It's sort of going to ignore the extreme values and just focus on the things near the center. But we'll get into this when the clusters move together and the softening of margins in a little bit. But another thing I want to talk about is, before we get to that, is this idea that SVMs, as I presented them here, where you're drawing a line through data, are sometimes not all that useful, right? So here's a particular data set where you have a clump in the middle and a ring on the outside, and I've drawn the best SVM fit for that right there. And that's just a horrible model for the data, right? The problem is that this data set is the boundary is inherently nonlinear. You can't draw a straight line that'll do a good job of separating pink from yellow. So the way SVM approaches this is by basically doing some sort of coordinate transformation. And let me give you an example of this. So let's assume that we looked at this function and we come up with a nonlinear transformation of this data. And the transformation we're going to come up with is taking the square of the first coordinate plus the square of the second coordinate and exponentiating the negative of that. And this is known as a radial basis function. So that's R right there. And to give us an idea of what's going on, we can plot this in 3D. So here's our data set looking straight down from on top, looking at the x and y values. And what we've added here is this z direction, this r direction. And you can see that by choosing that particular projection of the data, we can find a place where you are able to draw a straight line that separates it, right? So now, if we draw a plane straight through the center here and say everything above it is yellow and everything below it is pink, then we can do this. We can do this SVM with a linear separator. And so the problem though is that we had to know exactly what to do. We had to look at this data set and say, I'm going to compute the radius from the center and use that as our projection. So what can you do if you don't actually know what the center is? I mean, you could do a mean or something like that, but what SVM does, and this is really interesting, is that it has this way of using a radial basis function kernel, and what that means is effectively you're treating every single point in the data set as if it's a possible center. So we start with our two-dimensional data, our x and y. And then if we have 1,000 data points, we add 1,000 more dimensions to the data set, each of which is a radial basis function computed from the center of one point. Right, so in that case, we've, no matter where this center is, we sort of have that information that lets us draw a line in this very high dimensional space. Now, the first thing you're probably thinking is, that sounds ludicrous. If you have 1,000,000 points, then you end up with a 1,000,000 by 1,000,000 feature matrix, and it's probably really inefficient, right? And the answer to that is yes, that would be really inefficient. But you can do this thing called the kernel trick. And I would, if you're interested in this, look it up, because the kernel trick is so freaking cool. Because basically what it means is that you can compute the SVM in this 1,000-dimensional space. And actually, technically, you can compute an SVM in an infinite dimensional space without ever having to actually realize those infinite dimensions. You just use kind of a mathematical trick that involves the relationship between inner products in the infinite space and in the small dimensional space in order to fit exactly what you would do in that large dimensional space without actually having to compute those large dimensions. So that's as much as I'm going to say about the kernel trick. You should read about it, because it's like at the center of all of this, and it's really interesting if you're interested into digging into the mathematics about it. But what that means, that's all implemented in Scikit-learn. So if you say SVC kernel equals RBF, for radial basis function instead of kernel equals linear, then it's going to do that trick. It's going to fit the results as if it's computing a basis function from every point in the data set, but it's going to do it really, really fast. And the result is this. So it projects the result down. So by doing a radial basis function kernel, we effectively get that slice through the 3D projection of our data, and we can start to create even more intricate dividing lines between our data sets. And I forgot I didn't actually go into the softening parameter here, but there's if you adjust the C value, the C value basically tells you, if you have a small C value, it lets those margins kind of bleed into the distributions. And if you have a large C value, it tries to keep the margins really tight around the clusters. So you can see if I did C equals 100 right here, it doesn't let those margins pass any of the any of the points in the cluster. But if I have smaller C values, then those margins can sort of go past. And mathematically, what's going on there is it's just, you can think of it as a way to control. It just controls the cost function that's being computed and lets those points pass a little bit. And if you want to know more about the mathematics, I can point you to some resources on that if you ask me afterwards. But effectively, that's what's going on in support vector machines. You have this kernel that does some mathematical tricks to do things efficiently and lets you compute either linear or nonlinear dividing lines within your data set. Yeah. Sorry? Yeah, so support vector machines can do multi-class classification also. So that it's kind of the intuition is that it basically like treats, you can treat each class as a group that you're classifying compared to all the rest, and you treat each of those, you fit a different SVM for each of those, and you can kind of pull out the results that way. Yeah.
Apologies if you've already said this, but normally you have data in multiple dimensions, and it's very hard to visualize it unless you are doing dimension reductions upfront, right? So in those spaces, like how do you choose which kernel do you want to use, and if there is documentation or more insights?
Yeah, that's a good question. So he's asking in the cases where I don't have two-dimensional data where I can just visualize the line and see how well it's doing, how do I choose whether RBF or linear is doing a good job? Right? If you can't visualize this. And what that comes down to is these ideas about model validation. We're probably not going to get into this today, but you can dig in there or in the book that I referenced earlier. The general idea is that you leave out half of the data and you fit to the other half, and then you see how well your model performs on the holdout set. And by doing that, if I left out half of this data, I could see that this is a really bad model. Actually, since this is important enough, I'll show you real quick how we might approach this in Scikit-learn. So if I do from sklearn model selection import train test split, and I'm going to do x1, y1, x2, y2 equals train test split of my x and my y. And x1.shape, x2.shape, we'll see what they are. So, oops, I did this in the wrong order. I need this to be x1, x2, y1, y2. So now we have a training set of 75 points and a test set of 25 points. So I'll take my classifier like this, and I'll fit it on x1 and y1, and I'll do predicted equals clf.predict of x2, and then actually there's a shortcut to do this. So then I could do like y2 minus y pred. Actually y2 equals. I could do the mean of y2 equals y pred, and I see that only about 50% of them are correct. Whereas if I do an RBF kernel, it'll be 100% of them are correct, because this is a really simple data set. But there's something, if you don't want to do this sort of step manually, you can do something different. You can do clf.score on x2 and y2, and it'll compute that score automatically for you. So what this is doing when you call the score function, it's saying predict the model on this data and compare it to these labels and see how well you're doing. So now you can imagine doing something like, let's do this. C equals np.linspace. Here, I'm going to do it this way. 10 to the np.linspace minus 2, 2, 10. And I'm going to do for ci in C, tab all this over here, and do scores equals that. I'll do scores.append that. I'm going to do C equals CI, and then I can plt.plot C kind of scores. So this is a way that you could do this manually. And oh man, I think I need to do semilog x so we can see the scores. So you can see that there's some transition here where, I did this for linear, right? So let's do this for RBF so we can see better. So you can see that there's some transition here for some reason around 10 to the minus 1, a C of 10 to the minus 1. So you can think of that as like a scale that's important on the plot. So in general, when you're doing these sorts of things and trying to choose model parameters, you can play these sorts of games where you try fitting a number of models and see which one fits the best. Yeah.
If you don't mind the digression, what this predict function does, it's not a regression anymore because you haven't got a regression model. So what's going on with that?
Yeah, so the predict function here is literally just saying, like, if you're if you're on one side of the line, you're pink, and if you're on the other side of the line, you're yellow. Or in this case, it's 1 and 0.
It just binarizes the data.
Mm-hmm.
That's what class it's in. It doesn't actually predict a y value. Well, I guess it predicts the y value as a class.
Yeah, so if I look at this, ypred, in this case, since it's a classifier, it's gonna, the inputs were 0s and 1s, so the outputs will be 0s and 1s also. Yeah.
So for the nonlinear case, does it always overfit the training data?
Does the nonlinear always overfit?
If you go to, you can go up to an infinite dimensional space where everything is separated.
No, I wouldn't say it always overfits. It actually performs pretty well. It depends on the input data. Sometimes it'll overfit and sometimes it won't. And I don't know if that's a helpful. I don't know how to generalize more than that. Yeah. Yeah, so the question is, does it depend on the C parameter? The C parameter you can think of as sort of controlling the model complexity. So yeah, it does depend on that. And you can often, by adjusting the C parameter, tune that overfitting, underfitting. There's another question that I missed.
Can you just move up a little bit?
Oh yeah, sorry. This? Oh, up. Sorry, I have my scroll bar different than you do, I think. Yeah, so this is kind of like the basic type of model validation you can do. And if you're interested in digging a little more into model validation, there's another thing called cross validation, which I won't get into here, but hopefully Gael will talk about that a little bit tomorrow. Yeah. Yeah, that's a good question. Feature importance. So is there a way to evaluate how important each feature is in the classification? And the answer is that depends on what algorithm you're using. So what's that? For SVMs, for this, I don't think there is. No, there's not a very easy way to do that for SVMs, but I'm going to talk about random forests next, and that's one where it's pretty trivial to compute feature importances. So why don't we jump into that? So that was SVMs, and the nice thing about SVMs are the fact that it doesn't respond to outliers. It sort of treats boundary cases as the most important things. Another approach to supervised learning that's good to know about is this thing called random forests. And similarly to the SVM notebook, I want to use this opportunity to give you some intuition about what's going on in random forests. So first, to motivate random forests, this idea called decision trees. And decision trees are really kind of a basic thing. If you've ever played that 20 questions game, is it bigger than a bread box? This is how you can narrow down with just a few questions. You can narrow down on some very detailed categories. So, for example, if you're trying to build a decision tree to classify animals, you might start with with how big is the animal? Is it greater than 1 meter or less than 1 meter? And depending on the answer to that, you ask a different question. If it's greater than 1 meter, does the animal have horns? No. Is the animal wearing a collar? And yes. And so if you have an animal that's longer than 1 meter wearing a collar, then all of a sudden with just 3 questions, you've narrowed it down from the entire animal kingdom to something that's most likely a dog, right, in a lot of cases. And so these kind of questions, these decision trees can be really powerful because if you ask the right questions, you can basically reduce a really large space down to a very small space very quickly. Have you seen these little games that people have created where it like asks you think of something and then it asks you yes and no questions and you press the button, it's like shaped like an egg and magically it gets what you're thinking every time? It's basically a decision tree. They've created a decision tree. The hard thing with decision trees is coming up with the right questions. Like if you said, how big is the animal? Is it greater than 1 millimeter? Yes. Is it greater than 2 millimeters? Yes. Is it greater than 3 millimeters? Yes. You could ask a lot of questions before you get any useful information. So if you come up with the right series of questions in a decision tree, it's really powerful. So in machine learning, what decision trees are all about is the training step for them is coming up with the optimal questions. So in Scikit-learn, there's this thing called a decision tree that if we start with data that looks like this, we can, I have some code for kind of visualizing this. So in Scikit-learn, there's a decision tree that basically, as you fit it, it decides how it's going to split the data to ask those binary questions. And maybe at one level, it looks like this, and it calls everything above the line red and everything below the line purple. And then if you ask a second question, everything here is correctly identified, so it splits this bottom one. Everything over here is blue, everything over here is yellow. You ask another set of questions, and it creates another binary split in that path down there. And eventually, after just 5 questions, we've pretty well covered this entire space. And we have a nice decision tree. And what's going on inside this plot tree interactive is it's importing sklearn decision tree classifier. It's instantiating the classifier, and then it's visualizing the results of the classifier on this input. So I just kind of short-circuited all that code that's happening there. But the point is you have this series of 5 questions that lets you divide the space and then figure out a nice classification. Now, does anyone see some disadvantages with this approach right here? Where do you think the decision tree might go wrong here? Outliers, yeah. So, like if you saw, so right here, these red and purple are just sitting there in the yellow. Is that what you're looking at? Yeah, the red and purple is sitting in the yellow, so those aren't classified correctly. What about, what do you think the correct classification of a point right here is? Because right here, the decision tree is saying this should be a purple point, right? Because it's decided that this slice of the space is purple going all the way down here. So you have these really strange features like this whole strip being labeled purple, even though it's really far from the purple cluster. Right, and that's a feature that comes out in decision trees because they're essentially overfitting the data. We have this whole strip that just depends on the accident of this one point landing right there. So decision trees are really effective. You can ask a few questions and get to a very detailed classification, but they tend to overfit the data. They tend to make assumptions based on the noise in the data that aren't all that helpful for your results. And you can see this a little bit more if I took the first half of the data and the second half of the data and I drew the 2 decision trees that correspond to that. And you can see that with the first half of the data, it's saying that this whole strip should be purple. With the second half of the data, it's saying this whole strip down here should be purple. So depending on what subset of the data you're choosing, it's kind of coming up with weird classifications towards the middle. But there's some things that are consistent, right? Like this top part is red in both of these. This part right here is purple in both of these. So what this suggests is you might be able to take chunks of the data, like the first half of the data, the second half of the data, some other random sampling of the data, and fit a whole bunch of decision trees together and like average the results. Because on average, these right here are going to be purple almost every time. But the places in the middle where there's more uncertainty, that uncertainty will be reflected by the individual trees disagreeing with each other. Yeah?
It decided on the decisions to make as part of the algorithm.
Yeah.
Like a PCA that it's doing in order to find those splits?
Oh, it's using some sort of generally like an information criterion type of thing. So it's looking at one way you can, like an easy thing you could think of is you're deciding, if you have two-dimensional data, you're deciding whether you want to split vertically or horizontally. Let me go back to here so we can think about this. So let's say you want to decide, the red one is already 100%, but let's say you want to decide where to split here. And you have to choose first, are you going to split horizontally with a horizontal line, or are you going to split with a vertical line? And effectively what it's doing here is, you can think about it like, let's see. So just to simplify it, imagine you were trying to decide the best differentiator between this yellow group and this purple group right here. You could sort of compute the histogram along each dimension and see how much the histogram overlaps. Like look at the distance between the mean of those two clusters. And you can see that the mean of the two clusters is much farther apart along the x direction than it is along the y direction. So then you say, okay, I'm going to split along the x direction. And then you could come up with a criterion like, say, go halfway between the mean of the two clusters and call that the split point. And that's how you could choose it. Yeah, so it's doing these orthogonal decisions, and effectively that's what's going on. It uses some slightly more complicated statistics. It's using basically like there are different ways to do it, but you can use like an entropy-based approach where it's trying to minimize the overlap between the two distributions in an entropy fashion. But that's what's going on under the hood in the black box. Yeah. But getting back to this right here, the intuition that averaging different realizations of this decision tree could lead to better results than an individual decision tree is where random forests come in. So a random forest is a whole bunch of decision trees, each of which are randomized a little bit. So so looking at this, here's a random state, and what I've done is I've taken the x and y components that we started with, and then I'm shuffling these and taking the first half of the data. So it's basically choosing a random 50% of the data. And depending on the random seed, we get a bunch of different realizations of this data. So this is just a way of visualizing all those different random things. And what comes out is there are some things that are very consistent. The bottom left and right corners are always yellow. And there are some things that are very inconsistent. Towards the middle, we get different groups. And so what the decision tree, or what the random forest does, is it effectively computes all of these different trees and averages them together. And we no longer have to write for loops because that's all implicit in this black box classifier, the random forest classifier. And if I plot that, you can see the results of this. It basically conforms to what we would expect if we were trying to, by hand, draw lines in this two-dimensional space. It sort of finds yellow down here, blue over here, purple or red. And it does this by averaging out all these randomized trees. Now, one thing that's a little bit different, in the random forest classifier, up above, I was taking subsets of the data to fit different trees. You know, like like just taking different parts of the data. Down here with the random forest classifier, it actually uses the whole data set every time. But it changes the way that it decides to do the splits each time. So it'll kind of like perturb where the exact splits are being made by those criteria. And the result is a really nice classification with really relatively smooth, not orthogonal boundaries. Yeah.
I sort of see what you described here with these leaves, but we talk about supervised classifying, right? So this can be used for unsupervised, but then you have to develop these synthetic data to unsupervised classifying random forests. So how is Polytron working with synthetic data?
Yeah. So random forest isn't.
Mysterious, at least to me.
Yeah, random forest isn't generally used for unsupervised because you need labels in order for it to work. So unsupervised algorithms will be based on something different. So in this case, this is just a supervised algorithm.
But I know it's being used for unsupervised.
Oh yeah, that's true. You're right.
This is what I'm talking about.
Yeah. I'm not too familiar with unsupervised random forests. I could guess what they do is like you can, the same way you can compute a split criterion based on having two groups of data, you could compute a split criterion based on unlabeled data by trying to maximize some sort of non-Gaussianity. Like if the data are all kind of clumped together on one dimension, but they're bimodal on another dimension, then you might want to split on that bimodal dimension. So yeah, I've never used that. I don't think it's implemented in Scikit-learn, but it sounds interesting. Yeah. So I wanted to do one more example from the random forests. So this is random forest used for classification. It can also be used for regression, where you're computing not discrete labels, but continuous labels. And it's effectively the same idea, except when you get down to the leaves of each of the trees, you're averaging out the different predictions for what it will be and getting a continuous value out. So what it can do is if you're looking at data that kind of looks like this. So here what I did is I made a model that consists of a fast oscillation and a slow oscillation plus noise. And this is what the data looks like. And if I do a random forest regressor rather than a random forest classifier with 100 trees, and I fit it to the data and then predict it on a grid, what comes out is this right here. So it's hard to see, but the gray line is the true model, the red line is the random forest prediction, and the blue points are the inputs. And what's really interesting here is that the random forest is flexible enough to even pull out this like really complicated pattern in the data. Now you're not going to get from the random forest any sort of estimate of the frequencies that are happening here. Like you're not going to be able to inspect the model and the parts of the model itself, but you can get a really close kind of model in a predictive sense, where you can do a good job predicting what values there might be for intervening data that you add to it. So random forest can be really useful for this because it's almost like a non-parametric model. It can fit very, very complicated data sets. So as an example of that, let's take a look at random forest for classifying our handwritten digits. So similarly to before, this is what we looked at just before the break. We have our 64-dimensional digits, about 1,800 of them. And I'm going to do a train test split, and I'm going to use this metrics module that we haven't seen yet. train test split, and here's a decision tree classifier, fit it on the training sample, and then compute the predictions on the test sample. And our accuracy there for just a normal a decision tree with just one tree is about 84%. And we can compute the confusion matrix right there. So decision tree classifier, like we said, is not very good for, you can overfit the data, it's not very flexible. What I'd like you to do now is take some time and repeat this exercise right here with a random forest classifier instead of a decision tree classifier, and see what sort of accuracy score you can get on this test data. So see how well random forests can do on this data set. So I'll give you a few minutes to do that. It's nice to see how this can work. Yeah. No, I'm not going to get to hyperparameter tuning today. But if you go to the validation notebook, if you read through this one, this is where we'd get to it if we had more like 6 hours to work with today. One thing I wanted to mention, just as you think about it with random forests, one reason they're really useful is because they're incredibly fast both to train and to predict. Because they're based on this decision tree process that kind of like divides the data logarithmically. If you have n data points, it only takes log n questions before you get down to the details. And it's also easy to do massively parallel operations. So if you're working with a very big data set and a very complicated model, a random forest is something that can be evaluated really, really quickly and trained really, really quickly. Support vector machines, you can get really useful results similar to random forests, but the training cost is a lot more expensive, especially for these kernelized methods. Yeah.
There's been some effort to explore cost allocation schemes, especially how much bias by people here, I think, have published on it. I was wondering, the default in Scikit-learn, I think, is kind of random subsplit. I was wondering if you knew of, or if you had any thoughts on sort of like more, I know you can customize your cost allocation scheme, but whether you knew of any projects to sort of like kind of do some of that customization for you, or at least check whether your like CDAL scheme is like way off.
That's a good question. I'm not sure. You mean like actually validating the cross-validation scheme itself? No, I'm not sure about that. Yeah. I get the sense that there's some appetite for some much more deep dive into a lot of these things, and I'm hoping that Guile will be able to build on this and answer some of those questions. So hold that for tomorrow. Yeah, we only have a few minutes left here, so we're not going to be able to jump into that. So basically, with this, if you took a stab at this, you can replace decision tree classifier with a random forest classifier, and all of a sudden, just with changing that, your accuracy goes up from 84 to about 96. And playing around with things like max depth lets you kind of change things. So if your trees aren't deep enough, they get less effective in general. And so this is the kind of games that you can start to play when you're doing parameter tuning. Okay, so questions on random forests. I hope that gives you sort of an intuition for what's happened there, what's going on. All right, we're actually just about out of time. It'd be nice to be able to dive into these dimensionality reduction, clustering, density, and things like that. I'd encourage you, if you're interested in that, to take a look at those yourself. And in the last like 8 minutes or so, we can try to answer any other questions that might come up. Does anyone have anything else they want to bring up to the group or chat about? Yeah. Oh yeah, we mentioned the feature importance stuff. Yeah, we should talk about that. So if we take one of these classifiers, like I have this random forest classifier right here, and I do clf.featureImportances. What that actually is, so what the feature importances are in a random forest, and the reason they're so easy to compute, is because at every step in the tree, it's deciding which feature is going to be split on. So in the random forest, there's a really natural way to decide which feature is most important, and that is you count how many times you split on that feature. So this feature importance is, I think, does it sum up to 1? I think it does. Yeah, it sums up to 1. So this feature importances is basically a measure of the fraction of total splits in the random forest that feature was split on. So it can be, if we reshape this to 8 by 8, then what we have is kind of like an image of the feature importance pixels. If I do plt.imshow of that, and I need to turn the grid off. So this is kind of a visualization of, and I'm gonna add a color bar too. This is a visualization of how important the features are across these digits. So one thing that immediately jumps out is like stuff at the corner is not very, these pixels at the corner are not very important. And that sort of makes sense. Like the corner is not going to tell you much about what's going on in the image. But for some reason, these pixels, well, these pixels near the center are a little more important. And actually if you kind of squint, it sort of seems like stuff in this left quadrant and this bottom corner are the most important in classifying digits. And so you could, in this case, it's kind of hard to reason about that, but say if you were classifying MRI images kind of broadly, this might be an interesting way to look at what's most important in those images. You could see what parts of the whole picture are generally used to make those splits all the way down the tree. Does that help? Yeah. So these feature importances are nice, and random forests are great because it's a very intuitive explanation for what that is. With other algorithms, you can come up with ideas of feature importances, but sometimes they're a little bit more difficult to wrap your mind around. Yeah. Other questions? All right. Cool. Well, I think we'll break then. And thanks so much for having me this afternoon. Hopefully this was helpful. And I'm not going to be able to be around for the rest of the time because my wife is going to Europe, and I'm going to be home with my 2 little girls, which will be pretty fun. But I hope the rest of this week and next week goes well. So thanks. And Ariel is not here, so who knows what's happening next?
5-minute break or so, and then we'll come back for bids.